Okay, that robot voice indicates to us that the meeting is now live. Thank you very much for coming to the October meeting of the Von Braun Astronomical Society. I appreciate you all for coming. Now we have also quite a lot of people from Zoom. Hello Zoom, how are you doing? I hope you're doing well. Now tonight we have Dr. Kumar, who's going to be talking to us about comets. He is a postgrad working on comets at the University of Auburn. Now, I'm really excited for this presentation, and I hope that you all are too. So please, everybody, give a round of applause for Dr. Kumar.
Yeah. Thank you so much. So I'll just get started. So I tend to speak a little low volume, so in case I'm not audible or if my accent is too fast, just let me know. For the Zoom as well. So, okay, so today I plan to talk about comets, which is basically my area of research as well. So with comets, we dive deep into the solar system just by looking at them and trying to study them. We actually go back in the solar system. So
Oh, is it on? I turned it on.
I'll turn it off.
It's happened every single time.
Yeah, you just tested this before.
I did. Okay, I'll just move the slides for you. Whatever.
Oh, okay. Is this working?
It was working, and that makes me very angry. Wait, hold up now. Try now. Are you doing it?
Oh, okay, yeah.
Oh, it was
I'm
clicked
looking
out.
It's
I'm an
clicked
idiot.
out. Okay.
I'm an idiot.
So this is just the overview of my talk and how I'm going to go about it. So the initial slides will be like really basic stuff. So just bear with me. Introduction to solar system astronomy, the basic stuff, and a little bit more on the history of comets and asteroids, and a little bit of basics on how they evolve and what are comets basically. So after this, after that section, I would be basically focusing on comets, a little bit on techniques to observe and study a comet. So there are a lot of ways. Basically, in astronomy, all that we have is light. So we observe photons, as we say. So we use light or photons in different ways to actually take a good look at what the source is made up of. So there are different ways to look at it. So there are ground-based telescopes, different space-based telescopes, and what are the differences and pros and cons. I would like to talk a little bit on the Rosetta Mission, and then a little bit on how a spectrum of a comet looks like and how it is measured and what's it about. What's it about imaging the comet? And finally, I would like to touch upon my work. That is one project that I'm involved with is observing and studying comet 46P Volatile with the Hubble. So this again stopped working.
Did it really? Did it really? Oh my god!
I don't know. It somehow works from here.
Oh wait, does it? Try again. Okay, you just have to stand exactly right there. Otherwise, it won't work.
Okay. So a little bit on solar system astronomy. This is like very basics. The solar system basically consists of is driven by the sun, the star, and then the 8 major planets that you can also see in the model behind. And plus, apart from those 8 major planets, you also have small bodies or like smaller bodies that actually form during the formation of the solar system. So what are these small bodies? I mean, they can range from small rocks to huge dwarf planets. So even Pluto is now considered a dwarf planet, and now it's inside the small body class. They're basically remnants of planetesimals. So when I say remnants, so what happened is how they formed is it's when the planets were forming initially, those material that was left behind, that is what actually started forming these smaller bodies, and they started going around the sun after the solar system stabilized after a point of time. So that's why I code this as remnants. Okay, I can probably point here. Remnants of planetesimals. And by looking into those, we are actually looking into the evolution of the solar system, or the time where the solar system was forming. So there are two parts. One is the astro. So okay, let me explain it this way. So there are asteroids and comets. I'll come to the differences between them. Before that, the major orbits that these small bodies fit in, there are a lot of them, a lot of regions where asteroids and comets fit in. But then the major three orbits are the asteroid belt, Kuiper belt, and the Oort cloud. So what you see at the center is the disk. New pointer. So if you see at the center, that's where the planets sit, and that's basically the plane where the Kuiper belt is also there. So you have the asteroid belt, which is in between Mars and Jupiter. That's inside. It's not, you cannot resolve that. So asteroids come from there, and then the Kuiper belt is the disk outside here, and that extends into the Oort cloud. The Oort cloud is the big sphere that is there, that you see all around. So as far as the distances go, Neptune is about 40 AU. AU is basically astronomical units, the distance between Earth and Sun. So Neptune goes up to around 40 AU, and then right from there, all the way up to the Kuiper belt and the Oort cloud goes way beyond 20,000 AU, 50,000 AU. So that's the range of the entire belt. Yeah.
Yeah.
And so the objects coming from these, so basically asteroids and comets, more so comets, they can have, because they come from different regions, they can have different varying orbits. So those which come from nearby, like or what we call as Jupiter family comets, they have typically about 5 to 6 years, 10 years or so. And then you know about Halley's Comet, which is 76 years. So that is that comes from the Kuiper belt. So and then comets which come from the Oort cloud, they can have orbits as long as like more than 13,000 years, 18,000 years. So it'll just be a one-time visit. There are comets which you can see regularly, like in every 5 to 6 years. But then the comets which come from Oort cloud, they tend to basically come. It's like once in a lifetime chance to look at them. And the best thing about them is they have been in this orbit ever since they formed. And they actually formed in the plane, and then they were redistributed. So the material that is there inside has been away from the sun for such a long time. So when they come in and when we study them, we actually are looking at the material that formed way back during the solar system's formation. And that's also one really good thing about studying meteoroids, which are basically remnants of comets and asteroids. So that's a big motivation to study these. So, okay. Uh, okay. So comets and asteroids. Basically, this is what. So as I said, there's a very thin line of difference between comets and asteroids. Comets are basically icy bodies or icy rocks, which is surrounded by an atmosphere. That is, you look at the picture below. That's a comet. So that's actually a picture of comet 46P. And you see the green haloish thing, which is seen. So that is basically that's called the coma. And that's the gaseous atmosphere, gaseous industrial atmosphere. And the top picture is asteroid Vesta. So that's basically a rock. I mean, rock in the sense doesn't have icy volatiles as the comet does. So it doesn't look up. It doesn't show up as an as a fuzzy atmosphere when you look at it. So that's it. I mean, that's the difference, basic difference between comets and asteroids. So before going into the details, I just wanted to put this out. It's like comets. There's a theory that says comets came in and destroyed the dinosaurs. So it's again a theory. So, and then there are a lot of thoughts that went in when actually when people saw meteor. Even today, I mean, there are so many beliefs that when you see meteoroids, shooting stars are not comets, basically are meteoroids. We should start and so stuff, but it's just wanted to put them as. But then it was not until Sir Edmund Halley that we actually came to know about. I mean, comets were known way beyond. I mean, Halley's comet was initially the first observations date back to 250 BC, when the comet was initially observed. But then there were so many myths behind it, so many beliefs behind it. But then it was not until Sir Edmund Halley actually calculated the orbit based on the Newtonian mathematics and said that, okay, this is the object that will come again after this many years. And that proved to be right. I mean, he was unfortunately not alive to see that, but that was a fantastic discovery that comets are basically a part of our solar system and not something here, something coming out of something like that. And Professor Chan Wood, so that's he's the one who actually postulated the existence of Oort cloud that you saw in the image before, the sphere. So he actually ran basically extrapolated the available comet data and then calculated how many comets would come whose orbits are like longer than these many years, like maybe a few thousand years. So and then he figured out it is coming from everywhere. So one difference between the comets which come from comets which have a short period or like 5 to 6 years, they come from the plane, and these are coming from all over the place. So it also comes from at different inclination when you actually just like look at its orbit. So these were the genius minds behind comets. I'll
just do it.
Okay. So how does a comet look like? It looks like this basically. It doesn't look like this every comet doesn't look like this when you look at it using with your naked eye. But this was special. This was Comet Hale-Bopp and came in 1997. I don't know how many of you saw it in the sky. It was, I mean, that's what I was told, like I really did. But I was told that this comet was actually visible in the sky like for so much time. And you can actually see it with your naked eye. And that was something fantastic. So let me explain how this evolves, or how this is, what are the parts of it. So it basically has a head that's That's the center, and within it, so it basically starts out as an icy body. That's called the nucleus. That's inside this, that cannot be resolved because of the atmosphere. So and the atmosphere that's surrounding it, that's called the coma. And you see the whitish zone that's there. That is the tail, and that's the dust tail. And then the blue one, and that is the ion tail. So it has a dust tail and the ion tail. And the dust tail is curved because of the solar radiation pressure that hits on the dust particle, and then they take their own trajectory. And then the same with the ions. Once the gas is ionized, this should be in the direction opposite to the sun. So how does basically this evolve? How does the comet evolve? So when it comes closer to the nucleus, close to the sun. Nucleus comes close to the sun. I'm sorry. The surface starts heating up, and part of this, part of the solar energy is absorbed, and part of it is reflected. So there's a balance between that, and then that's what determines the surface temperature. And once it starts coming closer to the sun, the surface temperature increases, and there are a lot of volatile ices that starts to sublimate. So this, I'm talking only about comets and not about asteroids. So what I mean by volatile is ices which tend to sublimate super quickly. They are at different ices sublimate at different temperatures. So, and then once it starts coming super close, it forms an envelope. That's that which you saw in the previous slide as this one. So that's the atmosphere that is formed. That's called as the coma. And once this is formed, the gases actually start dragging the dust particles or lifting up the dust particles from the surface. And that's how the mixture of gas and dust actually forms. Okay, so that's about comet evolution, how it looks. So it doesn't. So only after the comet develops a coma, you can actually start detecting it. With better telescopes, you can do much better. But the start of the activity is when the comet starts to widen. So what is comet made up of? Basically water. Water is the main constituent of cometary ices. Apart from water, the second most abundant one is a mixture of carbon dioxide, carbon monoxide, and there are a lot of other minor components, including ammonia, methane, hydrogen cyanide, alcohol, and a lot of organics. And dust. So finally, dust is basically mostly it's silicates. So and then this is how when you look at a chunk of you can imagine looking at a chunk of ice and dust mixed together, and then create a ball, and then you throw that at you start bringing that close to the fire, it starts evaporating. So that's how it is. And that's how the comet itself is formed. So that was just an introduction. If you have any questions on the introduction, you can. Okay. Okay.
Now, did they find clays?
Clays. It's more like it's more volatile material than clays. I mean, it's kind of you can see more of that in probably asteroids or more rocky surfaces. So the surface, so the way the surface layers is in a comet, it's different. Mostly the first 2-3 layers are basically volatile ices, and then after that is what the non-volatile stuff comes in. So I'm really not sure about Okay, any other question? Okay, so observing comets. Let us look at how we observe comets. You basically need telescopes. You can actually see, you could have seen comet Hale-Bopp, but not all the other comets. So you definitely need telescopes to actually look at them and do science with them and study. So with ground telescopes, you can, I mean, most comets are discovered with smaller telescopes, like an 8-inch, like the one on the left. That's a small telescope, but with a smaller telescope, you have like a large field of view. So the best telescope to actually look and see if there is a moving object would be a smaller telescope, because you have like a huge field of view. And that's how like most comets are discovered with small telescopes. And one on the right is what this is a 1.2 meter, and this is a 50 centimeter. Both of them, they're in India, in a observatory called Mount Abu Observatory, and this is where I worked during my PhD, and studied most of the comets using these two telescopes. And below you have the Keck Observatory. So the telescope, and so the bigger the telescope you use, the smaller area you look into, but then you can resolve the nucleus of the. So you don't see nucleus from the ground-based telescopes. The only thing that you can see is the outer atmosphere. That's the coma. So in order to study the coma better, in order to resolve it, the ultimate goal, I mean, or one of the goals is to actually look at the atmosphere and see where in the surface that it comes from, where in the comet surface it comes from. So you use larger and larger telescopes. Now the next one, I mean, the Keck Observatory has amazing resolution. So it's basically we use larger telescopes and higher resolution instruments to have a better look into the coma, or into the properties of the comet, or the coma of the comet. We cannot have a close look at the nucleus, but then in order to look at the nucleus, we can actually go into space, because with space telescopes, you can do so many different experiments that you cannot do with ground-based telescopes. Like for example, the first one here, that is the deep impact spacecraft before launch, and so that mission was actually designed to go after Comet 9P Tempel 1, and this was in 2005. So what it had was, they had like an impactor. So when the spacecraft approached the comet, at a certain point, the spacecraft actually shot an impactor onto the comet. The aim behind that was to actually look at what is beneath the surface of the comet. So it actually, so those are the kind of experiments that you can do when you go into space and go do an in situ experiment. So the one on the right is the Swift Observatory, and the one on the bottom is the Hubble Space Telescope. With Swift and Hubble and the ones with the Space Telescope, you can actually also look at wavelengths, because you're in space, you're out of Earth's atmosphere. So you can look at wavelengths which you cannot from ground. For example, UV and like X-rays, gamma rays, and I mean, not for comets for sure, but then high energy stuff for other astronomical bodies. Even so, especially UV and infrared, we cannot. There's a window in infrared. So okay, I'll come to that spectrum part in some time. But then before that, so just to describe the pros and cons of between space and ground-based telescopes, both have their advantages and disadvantages. Starting with the ground-based telescope, the pros are you can build as much large telescope as possible. And it's becoming bigger and bigger now. And with bigger telescope, as I said, you can actually resolve the comet in a much better way, and you can actually study it in a much closer way. I mean, that's not possible with space telescopes, at least for now. It's also relatively easier to maintain because it's on Earth. You don't have to travel to space to repair it. Also, it has much lower costs. I mean, as compared to the space telescopes with the launch, stuff like that. But the cons are basically Earth has its atmosphere, and you cannot look at any source through the atmosphere without like it in all different wavelengths, and also you have like factors that are seen that come into place, and you cannot get clear images, and there's so many stuff that comes in. And also the sky coverage. So sky coverage, I mean, you need the sky coverage is kind of, I mean, it's much more easier with the space telescope, not much of a one. But then with the space telescopes, though there's no atmosphere, it covers as many wavelengths as, I mean, that is not being covered from the ground. And also you get very clear and sharp images because there's no atmosphere. But the con is the maintenance. So if something goes wrong, it's almost close to impossible to actually go and repair. I mean, it's possible, but still, I mean, it takes a lot of time and energy and money. So it has like extreme high cost, operation cost, and also time constraints. So there are both advantages and disadvantages to space and ground telescopes. So going into the spectrum, before going to a spectrum of a comet, I just put this slide so that you get an idea of what wavelengths we actually cover from ground. So it's basically the optical, that's the rainbow that is there. And then you have some parts of infrared, and that's all you can cover from the ground, and of course radio waves. But then there are windows where in far infrared, near infrared, ultraviolet, X-rays, gamma rays, all of that, which is not possible from the ground. And it's best if you go to space and look at it. So what I'm looking at is studying the comet in visible and ultraviolet spectrum. So that I mean, so as the coma is formed, it has a lot of gases. The ice is basically a mixture of different material, as I showed what a comet is made up of. So that shows up in the spectrum in different forms. So if you look at the okay, I'm sorry. Before going to that, I just wanted to know, because this is an observing section. I just wanted to show how a comet spectrum is acquired. Comet also, so another challenge in observing a comet and an asteroid is keeping the comet steady at one point. So if you're observing a star, or if you're observing a source, which actually most of the sources, other than the planetary sources, they follow the sidereal time. So you set the telescope at the sidereal way, and then you can just track it super easily. But then with comets and asteroids, they are moving objects. So in order to keep that comet on the slit, so you need to keep tracking the telescope at a different rate, which actually matches the movement of the comet. And for each of the comet or an asteroid, it differs. The one that you see below is the spectrum that is acquired as a raw image, as a raw spectrum. Like so when you look across from the row, that's which is the wavelength space. So each of these bright lines, so it's just one object that is split into the spectrum. That's basically by taking a prism or rating what a droplet does to a sunlight to get a rainbow. That's the same technique. So you get a dispersed light out of the single object. And so all of these different emissions, these are the ones that they're spaced in different colors or different wavelengths. So they actually indicate different presence of different molecules. So when you look at a spectra, so this spectra is exactly the one that is extracted from here. So so what we do is we add up the entire along the columns so that we get a better signal to noise ratio, and then you get this spectrum. So there are a lot of emissions, and you see this is basically the optical, that is from 4,000 to 7,000 angstroms, or 400 to 700 nanometers. And so this was actually taken with a 0.5 meter telescope with this kind of a spectrograph. So and you see the blue and the red camera. So the blue camera is one for the guiding, and the red is where the spectrum is taken. So there is a grading inside that, and one part of the light goes to the blue, which you see this part here, and then the red spectrum, and then the red camera actually gets the spectra. And so I don't want to go into how these emissions come in. Basically, there are different physics behind it, but I don't want to jump into that. But then you also look at when you look at a UV spectrum. So this is taken with the Hubble Space Telescope. So this is the spectrum of Comet 46P that I'll talk about a little later. But then this is how a UV spectrum looks like, and this is a near UV spectrum. You see a lot of OH here. So OH is basically a proxy of water. Water splits into H and OH, and mostly 98% comes as OH. And then there are different bands, and then there is CS, that's carbon sulfide. So also there is if you go beyond in the far UV, if you go in the shorter wavelengths, you see many more different molecules like carbon monoxide. See, there are a lot of CO lines. So by looking at different regions of the spectrum, you actually look at different molecules, or like you can actually look at the property of a comet by using like different wavelengths, and you can get a whole idea in a different way. So that's the importance of actually looking at different wavelengths and that spectrum. So now coming to imaging, imaging from the ground. So and I just wanted to show the difference between how a comet is imaged from the ground and in the space. So this is an image again from the 1.2 meter telescope in India. So these were the two comets. Now, if you look at space-based image, this is an image of the comet taken from the deep impact spacecraft just before its impact. So if you look at, this, and if you look at the so here you clearly see a nucleus dissolved, and if you look at if you look at this image, the difference is, it looks identical, but the difference is the scale of each of the pixels. So here, each pixel would be like thousands of kilometers. But when you come to space-based telescope, like the Deep Impact or Hubble or many others, you can have much better resolution. So this each pixel is just in meters. So that's, you can imagine the difference. You can actually resolve it in with such good resolution, and you can actually see the nucleus here, which is almost close to impossible when you're actually looking at from the ground. So I already showed you the next image, which is this is again the Deep Impact photograph after the impact hit the comet, and then there was like the outburst of material that happened. So this was the photograph that was taken immediately after that. So there's a series of photographs that were taken. So this is one of the famous photographs after that. So so that's the advantage of space-based telescopes. Okay, quickly coming to the Rosetta mission. Okay, before that, you have any questions on the previous section? Yes.
Do you have any idea how far the penetrator actually penetrated the instrument?
Oh, the impact was.
A few centimeters?
I have to look up the numbers.
I just.
Yeah, I think it should be in centimeters. I'm not sure what the numbers, but I can look up it. Yeah. Any other questions after that? Yes.
You mentioned telescope with large field of view.
Yeah.
Versus comets. One of you heard the Rosetta story. It's more like hyperspace.
What is it?
It's basically like a Smith castrating, but you replace the secondary mirror with a lens, with a specially designed corrector lens, and you turn your F10 Smith castrating to an F2.
Yeah. Okay.
And that gives you a really
Yeah.
and you still have the large actor.
Yeah, I mean, but that's still possible. Yes, definitely we can do that. Sorry. Yeah, I mean, you can still do that, but you're still limited at a certain point. I mean, you can. I mean, the smaller telescope you go. I mean, if you want to, I was just explaining the reason for that was if you want to have a large survey, a larger field of view would be much better. I mean, it's always possible to. I mean, if you do that technique, you're also losing a little bit of light with the focal reducer and stuff like that with the optics. But then for the survey, a smaller telescope with a large field of view is much easier. By the way, the LSST that comes in, that has a huge diameter, and also it's planning to actually look at a huge field of view as well. I think 9.8 degrees or something like that. So yes, of course. Okay, so going to yes.
We have some questions from Zoom.
Yeah.
This is from Tom. He's actually got a couple of questions in one. So get ready for an A, B, C, D, E here. Okay. So the first one is approximately how many Oort cloud objects have been identified having come from the Oort cloud?
Okay. I cannot say an exact number as of now.
Approximately.
It's definitely more than 1,000.
Okay.
Sure. I mean, the thing that Jan Oort actually did to actually postulate it was to extrapolate the number of comets that were known, and then he postulated about 10⁻⁹ comets coming from the Oort cloud. So that was the number that he gave, but it's not that everything is being found, or like we keep looking at it. But then, yeah, that's the number. Yes.
B. Okay. So we have, are all of these objects from the Oort cloud comets?
No, not really. I mean, the comets actually, as I said, it comes from Oort cloud. It comes from the Kuiper belt, that is the disk. So most of those are short period comets, which come from, like, say, within 200 years. So for example, Halley's comet is like 76. So that's
Well, Tom's asking about Oort cloud objects other than comets.
what's interesting.
Tom is asking about what is in the Oort cloud other than comets.
Oh, it's basically icy bodies that are there.
Yeah.
because the Oort cloud is at a distance of beyond 20 to 50,000 AU. There's no sunlight that is enough to actually. So it's basically extremely cold regions. So all of them are stored as, you don't see comets as comets in the Oort cloud. So when you travel to Oort cloud, the comets won't look the same as it looks when you're looking at it here. So they'll basically look as just like a ball of ice.
Rock.
As a icy rock or something like that.
C. Is the Oort cloud membership of an object defined by its estimated orbital period?
I'm sorry.
Are Oort cloud objects membership of an object defined by its estimated orbital period?
Yes, that is true.
Okay.
So the first thing is when you look at a comet is you try to get the orbit of the comet, and then once you know the orbit, you can actually find whether it's coming from an Oort cloud. Plus, the next would be the composition. Like Oort cloud comets are extremely active because they are coming very new. Only a few times they have come closer. So they have abundance of activity as compared to a short period comet. So the brightly, for example, Hale-Bopp is coming from an Oort cloud. That's why it has like a huge amount of activity.
Okay. And finally, D. What is your opinion about the possibility of extrasolar comets? Something from outside of our solar system.
It's not a possibility. I mean, it's definitely there. I mean, we already have two of them. One is the Oumuamua, and the other one is Comet Volatile. So
those are from outside of our solar
yes.
system. Oh,
So-
okay.
And so with LSST, there are oh, I'm sorry, Volatile. Comet Volatile is the second one. The first one is Oumuamua. So they are interstellar comets. So basically coming from outside the solar system. Yes, and there are objects which are going to which are obviously there, but then it's not detected. That's the thing. I mean, with LSST, they are expecting to detect a lot more interstellar objects.
Thank you.
So I'm going to the Rosetta mission. I just wanted to. So Rosetta mission was a space mission by the European Space Agency to go and study the comet 67P. And I just put up a mission timeline so that you can appreciate how much time it takes to actually go to a comet and get it back, or study that, or try to get a sample return. So initially it was planned as a sample return mission in '92. Then they changed it and redesigned it as an in situ experiment. So Rosetta has a orbiter that goes around the comet, and it also has a lander that actually landed on the comet. So there are instruments in both of them, the orbit and so orbit. The orbiter has the advantage of being in the coma itself, and the lander actually goes on and sits in the surface. So the lander was called Philae. So initially, this mission was actually planned to go to the comet 46P that I was explaining a while ago. But then they missed the launch window, and so rescheduled it, and now they had to choose a different target. So that's how the target 67P got chosen. And then they launched it in 2004. So it went into hibernation because, as I said, so this comet has an orbital period of 5.6 years. So you have to wait since 2004 launch. I mean, the next apparition or the next closest approach when the comet was coming into the solar system, into the inner region of the solar system was like in 2014. So the spacecraft went into hibernation and woke up back in Jan, and then finally Rosetta arrives at the comet in August 2014. Philae, that's the lander, it lands on the comet in November, and then this mission went for another 2 years. So the spacecraft actually orbited the comet for the next 2 years and moved along with it, which is phenomenal. I mean, we have a lot of results from that. And then finally, they ended the mission in September 2016 when they actually crashed the spacecraft itself on the comet. And then there are fascinating images from there. So yes, they did receive, like, until they were super close, until the spacecraft crashed, they still received the data. Yeah, and so the instruments on them. So as I said, there's an orbiter and there's a lander. So there are 11 instruments on the orbiter and 10 instruments on the lander, and all these are used actually to study the comet in detail. So this comet is one of the most well-known comets now. The surprising shape of the nucleus. I just put out a set of initial results. Surprising shape of the nucleus. That is this kind of a shape. That is a rubber duck shape. which was surprising because, as I said, we cannot see a nucleus shape from ground, so it's basically coma. So as they approached, this kind of a shape was surprising because it has two different lobes, and there are different theories that came in how they actually. So this defines how they actually formed and what was the possible time of formation, etc. Size of the nucleus was about 4 kilometers. Relatively, I mean, the net was very active, but relatively lower activity from water was seen in the neck region. Neck region is okay. I have the photograph in the previous slide, but when you look at that duck shape, the neck region was really active. By activity, I mean the outgassing or the volatiles going out. So the neck region was active, but then it was blowing water. So one thing that is one theory is that comets actually pour water to Earth. So we have to test what is the composition of water in a comet, because the comet is made up of water. So the P2H ratio has been measured in a lot of comets, and specifically for this one, it was quite higher as compared to the terrestrial values. So all of the previous measurements, this was the first actual in situ measurement. All the previous measurements were from the ground or somewhere else. So, but then asteroids, there have been asteroids which are actually found where water P2H ratio is much similar to the terrestrial value. So the theory has to it's still modifying it. So and then one of the major results were detection of volatile oxygen and volatile nitrogen. We knew that oxygen is present, but atomic oxygen was definitely found in the spectra, but then molecular oxygen was a new thing, and also extremely low magnetic field as expected. They did quote a value, but then it was like super low. So that's about the results from Rosetta. If you have questions, yes.
Tom has a question about the theory behind the sources of magnetic field.
Oh, okay. As such, the magnetic field should be 0 or should be extremely low, or in fact 0. But then the very low magnetic field which when I quote, it's basically they have calculated an upper limit for it, and they've quoted like an upper limit value, which is again, I mean, there's no particular explanation for the source of that kind of magnetic field. But yeah, I don't know. I cannot definitely answer that question right.
And another one, could comets like this deliver our atmosphere when Earth was forming? That was, yeah.
Sorry?
They were asking, could comets like this deliver our atmosphere when Earth was forming? Which
yes,
was one of the theories,
so
yes.
water?
Yes, I believe
Yeah.
that's what they mean.
Yeah, so that's what I was explaining. So water and other definitely when a comet hits Earth, or it would have hit. Definitely there would have been something that was brought up. That's what we are testing, whether the nature of water in a comet and the nature of water that we have on Earth, whether it's the same or not. That's why we measure the isotopic ratios. But as of now, they don't match. The asteroids match, not the comets. So yeah. But yes, comets can definitely bring something apart from the devastation. Is there something else?
No.
Okay. So finally, I would like to talk a little about Comet 46P that we observed through Hubble Space Telescope. So what was special about this comet? So initially, this comet was, as I said, chosen for as a target for Rosetta Mission, but they missed it. So when it was proposed that the mission, that the spacecraft would go to this comet, there were initially a lot of ground-based observations of this comet, and I think it was during the late 90s and early 2000s. That was the period when this comet was observed extensively, and there were a lot of results. So this is, but there was something special about this time around, which was its closeness. So it's a short-period comet. It's like, as I said, it's a Jupiter family comet with an orbital period of 5.4 years, and the last perihelion was 12th December. So when I say perihelion, it is the point which is closest to the sun. So in the orbit. And so it is known to be a hyperactive comet. By hyperactivity, it's a small comet, but then as compared to its size, we expect the activity to be low because of the small size of the nucleus. But then this shows a lot of activity. It shows a lot of abundance, a lot of activity. That's abundance in, say, like water production and other molecules as well. So the activity, the active area of the comet is like extremely high. That's how it's called as the hyperactive comet. So what's good about this time around was its close approach. It had a historic close flyby of Earth on 16th of December, and that was like just 4 days after the perihelion. So the reason it was also special was because it's close to the perihelion. So as I remember, if you remember, I said when it comes close to the sun, it starts becoming more active. So it was close to the sun, it was close to its perihelion, so it was in maximum activity, and it was also close to the Earth, so we could study it in a very detailed way. So because it's closer to the, so a comet, when it is like at a farther distance, you cannot resolve the coma as much, but then when an object comes closer, you can actually resolve it much more clear. So we could actually look into the inner 3,000 kilometers of the coma. So that was the reason the proposal was put in order to observe it using the Hubble Space Telescope, and we observed it in Jan. So observations. It was observed with 2 instruments on the Hubble Space Telescope. That is with the Cosmic Origin Spectrograph and then the Space Telescope Imaging Spectrograph. Both are different. Both instruments have different ways of. Both instruments are spectrographs, but then one is a slit spectrograph, like the one that I showed before. Then that was a ground. This was in space, and the Cosmic Origin Spectrograph it has basically a pinhole rather than a slit. But then it also, so they also differ in their resolution. The Space Telescope Imaging Spectrograph, that's called STIS, and COS. So STIS has larger wavelength coverage, but then low resolution. COS has a shorter wavelength coverage, but then extremely good and high resolution. The STIS covers both near UV near ultraviolet and far ultraviolet. COS has, you can see, look at the far ultraviolet wavelengths. So this was observed in the period like from 11th to 20th January. So this is like 1 month after the close flyby and perihelion. And that's because of the observing time that's like super rare in Hubble. So once you propose, you have like the time is extremely rare to get in Hubble. So that's also a reason that the comet was observed at that time. So the results, some of the results from both of the instruments were, one is carbon monoxide emissions were observed on cosmic origin spectrographs. This, as I said, this is a very high resolution one. So you see CO, CO2, but then CO2 and O2 was much less as compared to water. As I said, this is a hyperactive comet. Relatively large amount of sulfur. This was also very surprising because we're still looking at how what might be the origin of sulfur in comets. With STIS, we mainly looked at OH and CS. Remember the graph that I showed you, the UV spectrum, that was from STIS. So you actually see the OH and the carbon monosulfide emissions. That's found in the near UV spectrum. Surprisingly, no CO emissions were found as compared to COS, but then that also accounts for the resolution. It's not like really resolved. Now, one of the main results was the asymmetric distribution of water. We looked, because it's a long slit spectra, we could actually look at how the OH molecules are distributed along the slit. So that was found to be asymmetric in the coma. So those were a few results from 46P Hubble observations. And yeah, I'll end my talk. Yes.
No, okay. Rod asks, where did comets acquire the materials that make up their composition?
Okay, so it actually dates back to the formation of the solar system itself, as explained in the initial slides. These objects actually formed. It didn't actually form in the place where it is right now in the Oort cloud. It actually formed in the photoplanetary disk of the solar system. So when the planets formed, the remaining stuff, which could actually not form the planets, or which could not get into the gravitational influence of the major planets, that remained outside. So it basically, the composition comes from the initial solar system, or the photoplanetary disk that is there, and that also differs at what locations these were formed. So, for example, imagine the temperature of the sun at imagine the temperature of the disk close to the sun, and the temperature of the disk like far away. So those objects which form at the far away position, they have much more volatiles than the asteroids which actually form close. Yeah.
I wasn't aware of, but apparently there are lots of space telescopes,
Yes.
quite a few anyway. We've heard of Hubble coming toward its end,
Okay.
and they did a fix recently. What's the expected end now?
So Hubble has been there for like past 30 years now, and with everything going as planned, we can still expect at least another 5 years of age. And now the next big thing is the JWST, that's the James Webb Space Telescope that is going to go up. So that wavelength region is not exactly as Hubble. That is more of the infrared stuff. So Hubble covers UV and partly optical and a little bit of infrared. James Webb is more of infrared, but then that's the next big thing now. Yes.
Okay, got a couple. First one, oh gosh, there's more. Do short period and long period comets have different compositions?
Yes, actually, yes and no. So in long period comets, because as I said, they come from very cold regions, and they come very a few times as compared to short period comets. Their ices are less processed than the short period comets. So when you look at the basic composition is the same. When you look at a spectra, it will be mostly you'll see the major components like water, carbon dioxide, and the different organics. But then when you look at the ratios with respect to water, the production rate, the abundances, for example, like if you take cyanide, HCN, with respect to, we generally take, I mean, in order to compare the composition, it's the best thing would be to compare it with the most abundant one. So that's the water. So if you compare the ratios are quite different because the short period comets are processed and the longer ones are not.
Tom asked a question also about can comets be divided into families based on their spectra? Is there like a similar to like stars, I'd imagine? Is there something like that for comets?
It's not. I mean, classifying them based on their composition, as I said, it's not very easy because their basic composition is the same. It's basically made up of water and stuff like that. So when you look at a spectrum, it's the same. As I said, it's the same answer as previous. So it's actually much more easier to classify them according to their orbits. Yes.
And another one. Is it possible to associate a comet from its makeup to a particular planet?
I didn't get this, sorry.
Is it possible to associate a comet from its makeup to a particular planet? Could we tell, for example, what material a comet came from? Say if it was a Jupiter or a Martian.
So the comet actually didn't come from a planet. It actually comes from the remaining
Yep.
material that actually couldn't form the planet. But then we could, looking at the observations of looking at the composition, we can actually pinpoint, or we can at least try to pinpoint where the comets would have formed. So for example, if there is water actually sublimates at some region, and then whereas CO2 sublimates at a certain higher, so basically at a different distance because of the temperature difference. So they both sublimate at different temperatures. So now when you look at the ratios between the molecules, you can actually say where this would have formed, or where, I mean, it doesn't necessarily come from the source, but where in the solar system it could have actually formed. So that's what it is. Yeah. Yes.
Do comets experience mass loss because of the production of the coma? And does that mean like comets have a limited life?
Yes, absolutely. Comets do experience tremendous mass loss, I can say, when it comes closer. It depends on the activity as well. Higher the activity or higher the volatile. So if the comet is, so the comets are basically made of layers. So it's like it's like an onion layer. So the first layer will be volatiles. The first 2-3 layers will be volatiles, and then there would be just the rocks or non-volatile material. So the mass loss occurs super rapidly when the initial ices are exposed and how fast they're exposed. So that's why the short period comets have much less abundance than the long period comets. So because the short period comets come very quickly, like say every 5 years, so they keep losing their mass, including the dust and gas. So they definitely have limited amount of lifetime. For example, some of the comets, they cannot actually cross the perihelion because their orbits are such that they come super close to the nucleus, super close to the sun, and they just wipe out. The sun just wipes them out. For example, one example was, if you heard of Comet Ison, way back in, I think, 2012. So that was like, so sometimes you see comets becoming super bright because they are in such an orbit, and it's like super, they have like a lot of volatile. So we expected Ison to actually come out of perihelion, and we were thinking like, great, this is an extremely bright comet. We can do amazing studies with that. But then it went to perihelion and never came out. So that was a bummer. But then yes, so comets have limited lifetime. But then most comets will not go off in our lifetime. It'll take so many hundreds, at least hundreds of years, depending on its orbit.
So their lives are on the order of hundreds of years?
It depends. So some of them have lifetimes of thousands of years, many 10,000 of years. The ones which come from the outside sphere. But then the ones which are close by, they can have, say, a few hundred years.
Which is still relatively brief in astronomical terms. Does that
Yeah.
mean, so the new comets form all the time, and is there kind of a replenishing of comets every tens of thousands of years?
That's an interesting question. It's not the replenishing of comets cannot happen right now because unless there is like a influx of like too many comets together in the Oort cloud, probably maybe combining them together. But then once it comes into the inner solar system and starts losing mass, that's, I mean, it's almost can say it's not possible to actually replenish that particular comet.
I'm saying, are new comets always forming?
New comets, practically no, should not be forming. That's what, as far as my understanding goes, because the Oort cloud, the comets actually formed. It was much easier to form when it was just a disk as compared to now, because now the system has stabilized. The solar system has stabilized and everything is like running very smoothly. But in the initial period, everything was chaos. The planets were forming. Actually, the theory where how these comets actually got distributed. There's the theory of the initial planets forming, and then the planets were like initially Saturn and Jupiter didn't form where they are right now. They formed and then they started moving up and down. And then that actually disturbed the smaller bodies, which actually threw them out. So now it's not possible because now everything is stabilized. Unless there is some kind of a chaos that comes out because of the sun. Sorry.
Or a star passes close to the orbit.
Yes, so that's like a trigger. So that's not a comet forming, but that's what actually triggers a comet to come into the inner solar system. So that's basically comets are stable on the outer basically Oort cloud, but because that's one of the reasons when a closer star passes by, that has its influence on the comet and that kicks it off into the inner solar system. Yes.
Are there any asteroids that might be candidates for comets that lost all the salt?
Yes, absolutely. So there are seven. So as I said, the difference between asteroids and comets are very thin, and there are a set of. So there are a bunch of comets which do not show activity. Then you'll ask why they're called comets. That's because also classified because of their orbit. So that's like a very minor amount of them. They're called main belt comets, just like the main belt asteroids. Those are comets. Those are actually in a cometary orbit, but then they don't show activity. And there are asteroids which show activity, which is also a little surprising. So yes, comets, short period comets, or any other comet can lose its mass and actually become an asteroid.
Now, if you have something that's showing activity, like an asteroid with I guess a low eccentricity in its orbit, then wouldn't it just be perpetually having a tail?
Yes, it can form like they're also called, some of them are also called centaurs, if you've heard of them. So like a comet 29 feet, that goes into that never comes close to the sun as the other comets do. It's at an orbit of like it's at a distance of, it has an orbit of like 5.6 years or something. But then yeah, I mean sorry, the semi-major axis, the distance from the sun is almost stable. It doesn't, the perihelion doesn't come super close to the sun, but it still starts showing activity. So that depends on the amount of volatile material that is there. So that also actually links to where it was formed. So all of this basically links to the composition and then where it was actually formed, and if the comets were actually brought in, so it basically links to the formation. Okay. Yes.
I've got lots for you.
Okay.
Okay, so this one's from Tom. He has a question about the earlier comet spectrum slide. He asks, why are the peaks so broad?
Okay.
He asked if that was reality or the instrumentation.
Oh no, it is a reality. So,
Reality.
Yes.
I'm assuming it's not that one, but the next one,
Next one.
or the back
Oh,
one.
that one.
Back one. Back
Yeah. It's not.
isn't that working?
Okay. So yes, so as I did explain how these emissions are formed, they're basically fluorescence emissions. So when the gas, when you have different gas molecules in the coma, when the sunlight hits the gas molecule, for example, like C2, it excites it to a higher upper level, and then it de-excites, giving out an emission. So that's how these emissions are formed. Fluorescence is basically the main technique by which these emissions are seen. The reason for the broadening is because the emission is seen in, this is basically a low resolution spectrograph. And so when you resolve this spectra into a higher resolution, you'll see you'll see emissions in each of these wavelength bands. So when you combine them, because it's not resolved, that's why you see. But then the band is not coming because of the instrument itself. I mean it's a mix, because it's a low resolution, you're not able to see it. But then yes.
Tom, do you understand? Give me a thumbs up. Tom, give me a thumbs up if you understand, or a thumbs down, or do you have another question? Well, he's okay. I don't see you. Whatever. So let's move on. Can comets have cryovolcanism, basically water erupting instead of lava, instead of just like sublimation? Could they have like an eruption?
Yes. So there are jets that let me go to
Tom's good. He understands.
okay. Okay, this doesn't probably show. No, I mean, it's not a clear picture, but yes, so there are, then you see a lot of jets when you look at a picture. It's not the similar as a tail, but there are jets which form. You can, so those dust, those can be dust jets, or those can be actually gas jets, or like which come out. So that's more, I mean, it has been actually, there has been research specifically with Rosetta 670 how those jets come in. So there are different reasons. One is probably one of them was the collapse of a cliff on the surface. So it's more like that kind of an activity, not like an volcano or something like that.
I got another one. This is from Eric. When a comet passes through inner solar system and new surfaces are exposed and warmed up, do you observe new chemistry happening on the surface versus simply outgassing of components and compounds that were already there?
Yes. So what happens is, so when you say outgassing can only happen when the comet comes closer to the sun.
Yes.
So there is a specific, I mean, that's the general the trend that has been seen in the number of comets till now, that you see these I'll go back to the spectrum.
Forward, I believe. Oh, or is it back?
Yeah.
This one?
Sorry, no, back. I mean, this also is back.
That one.
So you see there is CN, there is C2, there is NH2 ammonia, there is atomic oxygen, and then in the next slide you see water, carbon dioxide, carbon sulfide. So the distances at which each of these emissions are seen are different. So the first one to appear is cyanide. The first one, yes.
But he's asking specifically about, is there new chemistry, or are they just like, are they forming new chemical compounds?
No, the general trend is, the general trend, except for some comets which really astonish us, like a comet called C2016 R2, so when you look at a spectrum of a comet, you always see this or this. You always, when you look at this, I can tell you this is a comet spectrum. But then that comet really surprises. In the optical, none of this was present, and it was completely CO plus. And then there was a lot of nitrogen, or N2 plus.
Which was an ion?
Ions, yes, and ionic emissions. So that kind of a comet. I mean, so we tried doing we tried investigating what's the ratio of the CO to N2 in that, and then trying to tie up, and then so it comes down to how the ices are basically trapped in the coma, or in the surface of the coma. So yes, I mean, in general, the chemistry doesn't change.
Okay.
Yes.
What sort of interactions are there with the charged particle from the sun to the solar wind? And is there any ionization of the comet's tail?
Yes. So the comet tail is. I'll go back to all the early slides. Oh, yeah. So yes, so this entire tail is filled with just ions. That's why it's called the ion tail. So what happens is the gas molecules here, once the coma is formed, the gas molecules are out. The molecules are out in the gas coma. When that interacts with the solar wind, and then that ionizes the gas molecules already present here, and that's how you see this bluish thing. So basically, this is a lot of CO plus, N2 plus, and a lot of other ions that is seen. So that's how. So the bluish thing is the ion spectrum is turned towards the blue end of the optical spectrum. That's how you see that blue. So it's, yes.
Okay, so we are out of time. If you have any more questions for our wonderful presenter here, our special guest, please stay after the show. At this point, I would like to thank everyone for coming.
Thank you for
Thank
your
you very
patience.
much. Goodbye, Zoom.
By the way, to let everybody know, we're gonna be having a star party here tomorrow night. No planetarium show, but we'll be meeting out in the field. So if you want to stop by and look through some telescopes or anything like that, or bring your own scope.
We do the first night.
Yeah.
Yeah, my email is right there in case you want to reach out to me later. So, yeah. But if you have any other questions now, also, I'm ready to answer any questions.
Just. a quick question.
I take it with me. Oh, you brought that.
Yeah. Early next year,
Yeah.
we're expecting.
I had
to
more than I-
Uh-huh.
About third and fourth day.
Order the next year. Tuesday next week, so.
Oh, good deal.
Yeah, those are 4 to 7.
Jeff? Jeff, that's right.